Okay, so today we are going to talk about the orthogonality of the Laguerre polynomials. Now, in the last lecture, we have actually I consider I take this Laguerre differential equation. Then I told you to find out the solution to this Laguerre differential equation, what we called as a Laguerre polynomials. Then we see the generating function and also some of the reconciliation for those regular polynomials. Now, today we are going to talk about the orthogonality of these Laguerre polynomials. Uh, the Laguerre polynomials, as I said, you can obtain those Laguerre polynomials from the solution, and also we can obtain those Laguerre polynomials from the Rodriguez formula that I'm going to do after this topic. I will just consider the Rodriguez formula and I will write down the different Laguerre polynomials. We also, I asked you last time to find out the Laguerre polynomials from the very general solution, from the solution to the Laguerre differential equation. But let us try to first find out the orthogonality condition of this Laguerre polynomials. What is the orthogonality condition for the Laguerre polynomials? So the orthogonality condition for this Laguerre polynomial is that we need to prove that from integral 0 to infinity e to power minus x some ln of x, that is a Laguerre polynomial of order n, and another Laguerre polynomial lm of x into dx. It's always given by this canonical delta mn, right? So that means this is equal to 0 for m not equal to n, and this is equal to 1 for m equal to n, right? So let us try to find out this orthogonality condition for this. Okay, how we will do that? Again, I'm just going to start with the generating function. You know the generating function for this Laguerre polynomial is given by 1 minus t e to power minus xt divided by 1 minus t, and this particular function will generate a Laguerre polynomial of order n, ln of x t raised to power n. That is the coefficient to this t raised to power n are actually the Laguerre polynomials. Similarly, I will consider for the another variable 1 divided by 1 minus s e raised to power minus xs divided by 1 minus s is equal to, it will again generate a Laguerre polynomial of order lm of x t raised to power s. Oh, sorry, t raised to power m, t raised to power n and t raised to power n. Fine. Okay, let us take the product of these two. So when I'm going to take the product, it will be like 1 divided by 1 minus t e raised to power minus xt divided by 1 minus t into 1 divided by 1 minus s e raised to power minus xs divided by 1 minus s. Fine. This will be equal to some summation over n, summation over, this is summation over m here, summation over m ln of x, lm of x, then t raised to power n, t raised to power m. Sorry, this is not t, this will be s raised to power m, t raised to power n and s raised to power m. Okay. Therefore, as we have done in the last case where we talk about the Hermite as well as the Legendre polynomial, what I will do, I will just multiply both sides on e to power minus x, e to power minus x, and then we'll integrate. So I will say therefore integral 0 to infinity e to power minus x ln of x. If I'm going to multiply e to power minus x here, and we'll integrate from 0 to infinity lm of x into dx, that will be then the coefficient of this integral will be the coefficient of t raised to power n, s raised to power m in the expansion of this very integral, that is in the expansion of integral 0 to infinity e raised to power minus x. Then I will say 1 by 1 minus t, 1 by 1 minus s into e raised to power minus xt by 1 minus t into e to power minus xs divided by 1 minus s into dx. So this integral is actually the coefficient of t raised to power n, s raised to power m in the expansion of this particular integral. So now I will consider this integral and I will show what could be the expansion of this particular integral. Okay, so let me say that, I'm saying that let this be I. So let us consider this very integral and I will show you the expansion. Okay, So I will say that this very integral, I will write down this as I will be equal to, uh, okay, I will just take these constants out. I will say that this 1 divided by 1 minus t into 1 divided by 1 minus s integral 0 to infinity e raised to power minus x, and in the integral we have e to power minus xt by 1 minus t into e to power minus xs divided by 1 minus s into dx. Okay, fine. See, what I will do, I will write down this integral as 1 divided by 1 minus t into 1 minus s, then integral 0 to infinity. I will take this e to power minus x out from all these terms. So here I will be left with uh, e to power minus x. It will be now 1 plus this is sorry, plus t divided by 1 minus t plus s divided by 1 minus s into dx. Just taking the out in this e because the base is same and the powers will be added. Okay, into dx. Fine. So what I will do now, this is of the form of like exponential of this. You know that e to power minus x exponent power series, it is like 1 divided by, okay, now I will take the integral of this very integral of this very integral. It will be now, you know that integral of this e to power minus x, it is 1, it is e to power minus x divided by into minus 1 into minus 1. So that will be 1 divided by e to power x. Now x का value जो है, then I will just substitute e to power instead of x I have this very value, this value. So what could be the value of this integral? The value of this integral will be now equal to 1 divided by 1 minus t into 1 minus s. Then I will write down this as 1 divided by 1 plus t by 1 minus t plus s divided by 1 minus s. This will be the value of this particular integral. Okay, so now let's try to further simplify it. I will write down this as 1 divided by 1 minus t into 1 minus s into, what I will do, I will write down this as 1 divided by, I will just multiply this throughout by 1 minus t into 1 minus s. So when you are going to multiply it by 1 minus t into 1 minus s, it will be 1 minus t into 1 minus s. Here it will be plus t into 1 minus t will get cancelled out. It will be t into 1 minus s plus here s, 1 minus s will cancel out. It will be s into 1 minus t whole divided by, I'm just multiplying the numerator and denominator by this. So it will be 1 minus t into 1 minus s. Now this 1 minus t and 1 minus s, this will go here in the numerator and it will cancel out with this term. I will be left with these terms only. Further, let's take the multiplication of all these terms. I will write down this as 1 divided by, it will be 1 into 1 is 1, and then minus s minus t plus st. Okay, it will be plus t minus st, then plus s minus st. Fine. Now this st plus and minus st will go, this minus s and plus s will go, this minus t and plus t will go, and I will be left with only 1 divided by 1 minus st, which I can write down this as 1 minus st raised to power minus 1. Okay, now from the binomial expansion I can have this is a minus b raised to power minus n. So I will write down this as, when the power series of this will be simply equal to, it will be 1 plus st plus st square plus st raised to power 3. Okay, sorry. Plus so on plus st raised to power r. I will say that. Right? Plus some r plus 1 terms, other terms, st raised to power r. So this is actually, so you can say that this is s raised to power n, t raised to power n, or instead of r, I will say that s raised to power n, t raised to power n, right? T raised to power m. Okay, now this m and n can take different values. So you will see from this here, as I said that this is the coefficient of this very integral. this is actually the coefficient of t raised power m in the expansion of this. So I have find out the expansion like this. So I will say that in which the coefficient of in this particular expansion, in which the coefficient of this t raised power n s raised power m is 0. It will be 0 if m is not equal to n, and it will be equal to equal to 1 if m is equal to n. So we prove that this condition, that the value of this particular integral, that is the coefficient of t raised to power n s raised power in this very expansion, it will be 0 for the case m not equal to n, and it will be 1 for m equal to n. So we proved out this condition. So you will say that therefore I write it here. So you can say that therefore this integral, that is integral 0 to infinity e to power minus x hn of x hm, sorry, not h, ln of x lm of x into dx will be equal to delta mn. So that is, this is 0 for, that means which is 0 for m not equal to n, and it will be equal to 1 for m equal to n. This is very similar to your previous two cases जहाँ पे हम the Hermite or as well as the legend orthogonality of the legend, and even in case for the this Bessel differential Bessel functions का जो हमने legend बोला ये किया था, Bessel functions का जो orthogonality condition हमने निकाला था. So this is about, so all you need to know about the orthogonality of the Hermite polynomial is this very equation. Okay, so you have to you need to know that this Laguerre polynomials are orthogonal to each other when this particular condition is being satisfied. Okay, fine. So let me now if you have anything to ask, okay, let me just finish this part Rodriguez formula, then we can discuss some about this particular lecture, then I will listen to your queries and the questions. But first let me just finish this quickly. Rodriguez formula. Rodriguez formula. Rodriguez formula for this ln of x. So what is the Rodriguez formula for this ln of x? It's simply ln of x is given by e to power x divided by n factorial dn by dxn x raised to power n e to power minus x. That means we can generate or we can have the different Laguerre polynomials of different orders from this very equation. Let us try to find out some of the Laguerre polynomials. I also told you last time to find out the Laguerre polynomials from the Laguerre solution. So the solution to this Laguerre polynomial was like, जहाँ पे मैंने आपसे कहा था, this is some summation n running from r running from 0 to infinity minus 1 raised to power r n factorial divided by some r factorial square, then n minus r factorial, right? और शायद मैंने s लिया था वहां पे, then x raised to power r. You can have the Laguerre polynomials. ये मैंने आपसे कहा था कि find few Laguerre polynomials. I don't know any one of you find those Laguerre polynomials or not, but if you find it difficult to find the Laguerre polynomials from this equation, we can also find out some of the Laguerre polynomials. Okay, let us try to find out some of the Laguerre polynomials from this Rodriguez formula. So let's suppose, for example, for n equal to 0, L0 of x. Okay, that means I need to substitute. So this for n is 0, that means this will be equal to e to power x divided by n factorial, that is 0 factorial, dn by dxn, that is this d by dx raised to power n, that is raised to power 0, that will be 1. Then we have this x raised to power 0 into e to power minus x. Now x raised to power 0, this is 1, this is again 1, e to power minus x into 1, this will be equal to simply 1. Same thing you can also find from this very equation. Okay, the first one is very quite simple. Let us try to find out the second Laguerre polynomial, L1 of x. Okay, so I have to substitute. So it will be e to power x divided by 1 factorial, then d by dx of n is 1, it will be x raised to power 1 e to power minus x. Okay, so this is simply e to power x then I have to find out the derivative of this very equation. So you can say that this is x e to power minus x into minus 1, okay, plus then e to power minus x. Fine, right? So now multiply this e to power x. अगर आप यहाँ multiply करोगे, when you will multiply this, it will be 1, then minus, it will be x e to power x into e to, that will be 1, so it will be 1 minus x.
1 minus
So the
x.
1 minus x. Fine. Similarly, I can find out L2 of x. So what is L2 of x now? L2 of x will be now e to power x divided by 2 factorial here, then d2 by dx2 of x raised to power 2 into e to power minus x. Fine. So what I will do, this e to power x divided by 2 factorial is 2. I will write down this as, I will just take the first derivative. I will write down this as d by dx of, okay, x square. I will write down this as such, then e to power minus x into minus 1, because differentiation of minus this, plus then e to power minus x into 2x, into 2x. Fine. Okay. Then what I will do, plus okay, this is it. Fine. Now taking the second derivative, I will write down this e to power x by 2 again as such. The second derivative is like, I will just write down this e to power x square as such. Differentiation of e to power minus x is e to power minus x into minus, that will make it plus. This minus 1 into minus 1, it will make it plus, plus, okay, e to power minus x मैं यहाँ पे as such लिख रहा हूँ. Then but it will be minus here, huh? Minus is already there, minus e to power minus x into 2x. Fine. Plus similarly here it will be 2x e to power minus x into minus 1, plus uh, plus 2 e to power minus x into 1. Okay, let me just multiply by this e to power x. यहाँ पे मैं multiply पहले इसको कर रहा हूँ उससे. So I will write down this is 1 by 2. This will be x square e to power x into e to power minus x. It will be 1 plus, sorry, minus, this will be 2x. This is again will be equal to 1 plus, okay, this will, sorry, it will be minus 2x, minus 2x, okay, minus 2x plus uh, e to power x into e to power x, it will be 2 plus 2 plus 2. Fine. Minus 4x. Fine. So it will be now, I will write down this as the equation. I will write down this as 1 by 2 into, this will be now x square minus 4x plus 2. So this is L2 of x. Similarly, you can find out L3, L4 of x. I will just write it down this L3 of x here, but you prove it. Huh? You take the three derivative. L3 of x will be now equal to 1 by 3 factorial, or you can write down this is 1 by 6. This will be equal to 6 minus 18x minus 9x square minus x cube. ये आप प्रूव करिएगा यहाँ पे. Similarly, L4 of x will be now equal to 1 by 4 factorial. Then I have 24 minus 96x plus 72x square plus minus 16x cube plus x raised to power 4. Okay, so on and so forth. You can find L5 of x, but you don't need to find all those, because it, the जितने आप higher values लेंगे, higher order, that you have to take those, that bunch of difference. Okay, so in order to find out these higher order derivatives, derivative of an nth order, I suggest to you to just Google or just go through any book. You will find a theorem, Leibniz theorem. Leibniz theorem. ये आप study करिएगा, because it will help you in finding out all these polynomials from the Rodriguez formula, whether that is Laguerre polynomial or that is this Legendre or Hermite polynomial, you can find out once you will memorize this Leibniz theorem. You can find out the derivative of any order, 1, 3, 4, 5, so on and so forth. So this is about the Laguerre polynomial. So we discussed about all the things. I didn't find out the proof here because I want you to concentrate on only this part. We can also find out the proof by exploiting this Leibniz theorem. I can have the Leibniz theorem, that is I can take this ln of x. Let me show you how you can do that. See how I can find out that, since it's e to power x divided by n factorial dn by dx raised to power n, then x raised to power n e to power minus x. Okay, so by Leibniz theorem, what could be the derivative? E to power x divided by n factorial will remain as such. And when you are going to take the nth derivative of this particular from the Leibniz theorem, it's always given by x raised to power n, then minus 1 raised to power n. You have seen अभी जो Rodrigues formula मैंने किया था, in the first case I have, if n is odd it will be minus 1, if n is even it will be plus 1. So depending upon the value of the n, so it is x raised to power n minus 1 raised to power n, then e to power minus x. This will be the first derivative. Plus the second will be now n into n minus 1. Okay, so sorry, n into x raised to power n minus 1, because the order of the variable will go on decreasing. The second will be now n minus 1 x raised to power n minus 1, because e to power x will remain as such, and also minus 1 raised to power n minus 1 e to power minus x. This will be the second. Plus the third will be now n, यहाँ पे आपका होता है 0 फैक्टोरियल, यहाँ पे आपका होगा 1 फैक्टोरियल, यहाँ पे n into n minus 1, right? N into n minus 1 divided by 2 factorial, then again n into n minus 1, again n into n minus 1, then minus 1 raised to power n minus 2 now, and x raised to power n minus 2 into e to power minus x. Similarly, I will have n into n minus 1 into n minus 2 divided by 3 factorial into n into n minus 1, right? N. So this is not here. N into n minus 1 only. There is some correction in my note. So n into n minus 1 by 2 factorial. Other will be n into n minus 1, n minus 2 divided by 3 factorial. N minus 1 raised to power n minus 2, x raised to power n minus e to power x. Plus so on. जो last वाला आपका होगा, it will be n factorial e to power x, e to power minus x. n factorial e to power minus x, because जो x raised power n का हो, it will be x raised power n minus n, that is 0, because it is goes on increasing, n minus 1, n minus 2, n minus 3. The last one will be now simply n factorial, because यहाँ पे आपका हो जाएगा n into n minus 1, n minus 2, n minus 3, n minus 4, so on up to the n. So that is n factorial divided n into n minus 1 factorial. यहाँ पे n minus 1 factorial आपका आ जाएगा. That n minus 1 factorial will get cancelled out with this, and we will be having the n factorial only. So it is n factorial e to power minus x into this. Fine. Now you can just from this equation, I can just write down this as, agar for example, if you take e to power minus x, you can write down the other Laguerre polynomial from this very equation. But if somebody is interested how we actually how we can have the Laguerre polynomials from this particular equation, that is how this will generate my L and X. If somebody is interested, he can do this proof also. So let me write this one, e to power x divided by n factorial. यहाँ पे आप e to power minus x throw out हैं, so I will take this common. So यहाँ पे आपका क्या रह जाएगा फिर यहाँ पे, it is minus 1 raised to power n. Fine. Then I have x raised to power n. Let me write this 0 factorial, plus now I have n uh, n x raised to power n minus 1, x raised to power n minus 1, या उससे पहले minus 1 raised to power n minus 1 में लिखूंगा यहाँ पे n in minus 1 raised to power n minus 1. Then I have n. Okay, what I will do here, I will just multiply the numerator as well as the denominator by n minus 1. So I will write down this as n n factorial. यहाँ पे भी मैं n factorial multiply करूंगा और यहाँ पे भी मैं n factorial multiply करूंगा. ठीक है, that I can do it in the next step similarly, but just to omit one step, यहाँ पे भी मैं n factorial multiply करूंगा इसमें, और यहाँ पे भी मैं n factorial minus करूंगा, right? Okay. Plus so on. Similarly, you can say that minus n into n minus 1 divided by 2 factorial into minus 1 raised to power n minus 2 x raised to power n minus 2. Then I will have अगेन n फैक्टोरियल जो मैं मल्टीप्लाई करूंगा. सो यहाँ पे प्लस सो ऑन, यहाँ पे e टू पावर माइनस x, यहाँ पे खाली आपका n फैक्टोरियल बच जाएगा, राइट. नाउ दिस e टू पावर x into e टू पावर माइनस, दिस विल बी 1, so I will have only the one n factorial, right. So now I am going to multiply with this n factorial inside. So how I will write down, I will write down this is minus 1 raised to power n, then n factorial जो मैं मल्टीप्लाई यहाँ पे कर रहा हूँ, यहाँ पे आपका n factorial into n factorial, ये n factorial स्क्वायर हो जाएगा आपका यहाँ पे, ठीक है. दिस इज n फैक्टोरियल में यहाँ पे मल्टीप्लाई कर रहा हूँ, ठीक है. Okay, n factorial. Now see what I will do here in this particular step. Let me write down this here, since this is n into n factorial divided by n factorial. Okay. Now what I will do, I will write down this as n, then I will write down this as n into n minus 1 factorial, right, divided by n into n minus 1 factorial. और जो ये n factorial आपका है, I will going to write down this as n into n minus 1 factorial. Now this n and n will go cancel out. No, I will do it other way out. See what I will do, यहाँ पे ये समझेगा, यहाँ पे फर्स्ट पॉइंट तो ठीक है, यहाँ पे कोई दिक्कत नहीं है, बिकॉज यहाँ पे सिंपली मैं n फैक्टोरियल से मल्टीप्लाई कर रहा हूँ. यहाँ पे मेरे पास है जो, यहाँ पे मैं इफ आई एम गोइंग टू मल्टीप्लाई n माइनस 1 फैक्टोरियल, हाँ n माइनस 1 फैक्टोरियल में यहाँ पे मल्टीप्लाई करूंगा, नॉट n फैक्टोरियल. इस वाली टर्म में n माइनस 1 फैक्टोरियल में मल्टीप्लाई करूंगा यहाँ पे, और यहाँ पे भी मैं n माइनस 1 फैक्टोरियल मल्टीप्लाई करूंगा. अब उससे मुझे क्या क्या होगा, सी what I will get here. Okay, so just a minute. I will write down this as n into n minus 1 factorial divided by, this is n into n minus 1 factorial into n minus 1 factorial. This n and n will go cancel out, so this will be n factorial square. यहाँ पे मेरे न्यूमरेटर में खाली n factorial बचना चाहिए. It should be like minus 1 raised to power n minus 1, then x raised to power n minus 1 into n factorial divided by, running out of time, divided by n minus 1 factorial square. इसका square आ जाए into 1 factorial plus, I will just check it, plus so on. यहाँ पे n factorial divided by n factorial जब आप इससे multiply करोगे, it will be simply n factorial divided by n factorial. Okay. Now we have some issues with this equation. n into n factorial, यहाँ पे हमने इसको सही लिखा है, यहाँ पे n into n minus 1 factorial, n into n minus 1 factorial. Anyways, I will just check it because we are running out of time. ये मैं देख लूंगा क्या दिक्कत है इसमें. I do not want to waste time here. But this is for some extra. If you are not interested in doing this proof, we can prove this that this will generate the ln x. Okay. From this very equation, you can simply write all these terms like, you can say that this is summation r running from 0 to infinity. Then I have minus 1 raised to power r. So I'm just taking instead of n minus 1, I'm taking this as minus 1 raised to power r, because r can take the values from 0, 1, 2, so on. Then n factorial divided by r factorial square into n minus r factorial. Okay. I will just check it what is the issue with, because it's not, the proof does not lie anywhere in any book. इसका proof जो है, you cannot find this proof. All the books like Arifkin and even this P.K. Chattopadhyay, they have directly write down this Rodriguez formula. They have not tried to find out the proof for this. And I tried to find it from many books, but I didn't. Okay, this was what I was trying to find it myself, but there is some issue with this particular equation here. Rest of the parts are same, but I will check it out. That's why I didn't ask you to do it. But if you go through any book, you cannot find out how they have proved it. They have directly write down this Rodriguez formula, and then they find out that this from Laguerre polynomials from this very equation. Okay, still I will just check what is the issue with this thing here. But till then, you just concentrate on this particular this. You can we can have the this Laguerre polynomials from this very equation. Okay, so this is everything about the Laguerre polynomials. Also another kind of a special function, and we are almost done with this special kind of function. Except we have now two different kind of functions. One is spherical Bessel function, and then there is the spherical harmonics. Inshallah, we are going to talk about these two things in the next lecture. Ja- and with that, we are going to end this unit. Okay, now uh, let me first stop it here. Then I can take your questions.